What's going on, y'all? This is Jeff. In this video, we're going to talk about what is multiplication. We're revisiting multiplication because I find that so many folks get stuck from bad experiences in math class and memorize multiplication as a procedure rather than a set of ideas. To address this, we're going to actually address the question, what is multiplication, from multiple perspectives or multiple representations. Prompt we're going to use here is, let's use abuelita language, which is another way to say simple language that you can talk with your abuelita or grandmother about. And we're going to use that type of language to describe what we see in the multiplication problem below. So here we have the symbols, 3 plus 3 plus 3 plus 3 plus 3. There are 5 3s, and we say that's the multiplication problem 5 times 3. And the quote unquote output of that problem is 15. Now, this is a representation of the underlying problem, 5 times 15. Some folks would say that the answer to this is simple. It just must be 15. No ifs, ands, or buts about that. I want to extend that and really push against it. In particular, we're going to use this multiple representations framework that I like to bring into math class to challenge the idea of math as a procedure. I like to say that math is a whole group of ways to think about it. And if we can approach problems from multiple representations, many, many different ways of addressing the same problem, if we get in that habit, we begin to think creatively, flexibly, and address problems from multiple perspectives, which gives us a lot more fluidity, both in mathematics and in external life. At a beginning level, I like to use the concept of VANVIS, so verbal representations, both abuelita and nerdy language. The second V is a visual representation, so can you draw pictures? Interest and intrigue, meaning that when we're studying mathematics, are there questions that come up? Can we address those concepts with inquiry, mindedness, and curiosity? And then the last is symbolic representation, which is usually the start of where math teachers think about math, but I think that that's the last of all these other representations. So we'll use this as kind of a rubric. Let's get started here and kind of pay attention to what we see. We're addressing the multiplication problem 5 times 3. We see in this particular situation that we've got this sum of additions, and each 3 is represented by boxes. So if we looked at the first 3, we might say when we add the first 3, which we'll represent in green, to the second 3, which we'll say, oh, okay, well, maybe we call the second 3 blue. So those two together become 6. And then the third 3, maybe we do that in pink, real mathematicians graph in pink. So here we've got the next 3 down. So 3 plus 3 plus 3, those 3 show up, 1, 2, 3 groups of 3. Maybe we'll go down to the next one, which we'll do in orange. So now we've got 1, 2, 3. And the last one, maybe we'll do in yellow. And check this out. The claim that we're making here is if we count all units where we take 5 groups of size 3, so the problem five times 3 is a counting problem. And what we mean by this is we are literally counting objects. Okay, well, let's kind of figure out what objects are we counting. Here, we count 5 separate groups, each of which has 3 objects in it. So this multiplication problem counts the total number of objects when we take 5 separate groups, each of which has 3 objects. This is the total number of objects when counting 5 groups, each of size 3. Well, we can abstract away from that. So in other words, multiplication counts a certain number of groups, each of which in the same size. But I would say that there's a further representation of multiplication. So we have multiplication as a counting problem. There's our abuelita description. We started to really develop the concept of number of groups and size of groups. But I would say something else here. Multiplication also counts the number of times we add a number to itself. So this is a second way to describe multiplication. Multiplication of 5 times 3 counts the number of times we add 3 to itself, right? Because 3 plus 3 plus 3, so there are 3 added to itself 5 times. 3 added to itself 5 times. So now there's 2 different ways that we're thinking about multiplication. One of them is to count the total number of objects. The other one is a count of additions. And we're saying that when we add 3 to itself, when we do addition 5 separate times, we end up with a total of 15 separate objects, and we can actually map those. Now, this is where, so we've kind of described what we call abuelita language. We're starting to get an intuitive grasp of what multiplication is and different ways to think about it. We have a visual representation for sure. I have my first question that comes up from this. I'm starting to get interested or intrigued by this information, which is, well, okay, I know that 5 times 3, based on this analysis, we just said that that's counting the number of times I add 3 to itself, but how is it different? I'm gonna go ahead and write this in red. How is 5 times 3 different than 3 times 5? In particular, what we've just said is that 5 times 3 is equal to 3 plus 3 plus 3 plus 3 plus 3. And I know that's 15. I also know that 3 times 5, that must be equal to 15. But my question is this, I don't know, is this equal to the same thing, 3 plus 3 plus 3 plus 3 plus 3? Or is 3 times 5, 5 plus 5 plus 5, which is 15? In other words, when I'm thinking about multiplication as counting, do I, which of these numbers represents the thing that I'm adding, or the number of the size of each group, and which represents the number of groups? And I think from this standpoint, like, this is where we might want to get into what we call a symbolic representation and start thinking about the anatomy of multiplication. So we're going to go ahead and call this the anatomy of multiplication. And we're going to start getting a little nerdy here. So multiplication for each multiplication problem we have a few pieces. Okay, so let's go ahead and look at those pieces. And we'll use our example that we started with. So let's write 5 times 3 equal 15. This is what we call the multiplication symbol. You could also call this dot, the multiplication dot, D-O-T. or symbol. Sometimes people use the times symbol depending on what you want. So you might call it the multiplication dot symbol. That's the thing right in the middle. And then we're going to call any part of a multiplication a factor. So we're going to say that a part of a multiplication is a factor. Do you see the nerdy language coming in? This is no longer abuelita language. I think that if I started saying multiplication dot symbol and factor to my abuelita, she might tell me to stop cussing, right? So we're going to say that a factor is one number in a multiplication problem, or a part of a product. And we'll talk about that. So here we see that this multiplication problem actually has two factors. We say that it has the left factor. So 5 is what we call the left factor because it's literally to the left of the dot. Could you guess what we call the thing to the right of the dot? Ding, 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 ding. You got it. This is what we call the right factor. So the left factor is the thing on the left. The right factor is the thing on the right. Here we've got the multiplication symbol. And then in any multiplication problem, we say that the output is called the product. So the product is the output of a multiplication operation. Okay, so now we're starting to get a little bit more, I don't know what you want to say, advanced or technical, because we're no longer just thinking about these two problems as the same problem. I do agree that the product is the same, but if you look at the anatomy of these, the left factor is not equal to the right factor. Excuse me, the left factor here is not equal to the left factor there, meaning that these are actually two separate problems. And the question is, do we impose the same interpretation on those problems? I actually might, in this case, talk about what I want to call left multiplication. Which is, if I have a number, take an object, I suppose what we want to call it, and multiply on the left of that object. So here, when we had the number 3, this was a given number. If I left multiply 3, so there's the multiplication dot symbol. If I left multiply 3 and I hit it with 5, this is going to be a left multiplication of 3 by 5. And we're going to impose the interpretation in this particular discussion that when we left multiply, the right number, the right factor represents the size of each group, and the left factor represents the number of each group. So when we left multiply, let's assume, do we have to assume this? No, not at all. We could have switched the representation. We could have said, when we left multiply, let the left one represent the size of each group and the right one represent the number of groups, except generally when I look at a number, I like to think about counting. So the number 3, I'm thinking I have groups of size 3. And then when I hit it on the left with a 5, I think, oh, okay, well, how many groups of size 3 do I have? I have 5 of those. So if I start with a number 3 and then I multiply by 5, then I'm thinking I have a group of size 3, and then I take 5 such groups and I want to know what's the total number of groups. So when we left multiply, let's assume that the size of each group is captured by the right factor, and the left factor represents the number of such groups. Okay, so all of a sudden, when we go back to this problem, yeah, who knew? Do you see this? Most people say that this is not the answer. Like all this work we're doing, a lot of teachers wouldn't give you credit for this, but here's the deal. I find the answer to this completely boring. And in fact, it doesn't actually extend our knowledge or our creative thinking. So I would actually challenge somebody that says a student that can produce 5 times 3 is 15 knows this math. I would say that a student that could describe the anatomy and functionality and interpret in multiple ways what's going on with this, not only will they be able to get the answer, but they'll also have a lot more flexibility and strength in understanding this. And this is what we're going to do over and over and over together in this class, which is extend your understanding of what it means to learn math, really challenge that negative mindset that so many math teachers propagate, which is math is all about answers. I would actually claim that math is all about exploration and inquiry. And that's what we're doing when we kind of represent it in this way. Okay, let's get back into this and try to answer our fundamental question that we started with. Let's go back to our inquiry that we had, this kind of inquisitive nature here. When we said, how is 5 times 3 different than 3 times 5? We now have a standpoint from which we can analyze this. First of all, 5 times 3 is different from 3 times 5 because the left and right factors are swapped. So here the left factor is 5, here the left factor is 3, and then the right factor vice versa. Here the right factor is 3, here the right factor is 5. But we also have a different way to think about this. So let's go back to this thing that we just said. So let's start with the number 3. Start here. And then we're going to left multiply. So the left factor is 5. In other words, what we've just done is we've left multiply. And then we said that the product was 15. So this was what we said the product. And what we did here is we counted 5 groups of size 3 in each group. Okay, well, what if we were to actually kind of flip it? So this was the right factor is where we started. What if we said 5 was the right factor? So here, the right factor that we were going to start with is now 5. It's no longer 3. So we're going to start there. And then we're going to multiply the right factor on the left. So we're going to do left multiplication by 3. So now all of a sudden we're defining what the left factor should be. So we call that left multiplication. And we say that the product is 15, but it's not 15 because it's the same problem. It's 15 because 3 times 5, we count 3 groups of size 5 in each group. And we can actually visualize that. Notice that in this second problem, we're left with a different scenario, and we might as well use different colors to represent it. So here, the first group of size 5 shows up there. We'll go ahead and go to red. So the second group of size 5 shows up 15s. And the third group of size 5 we'll do in kind of dark blue, shows up at the bottom. Notice the 2 products are the same, but the way that we interpret those 2 products is different. This problem, 5 times 3, we say that it's 15 because when we count 5 groups of size 3, we have 15 units. This problem, 3 times 5, is also 15 And that's because when we count 3 groups, each of size 5, we get 15. So there are 2 different ways to reach the same output. This is kind of valuable in future. We're going to talk a lot about kind of how to represent this. And in fact, you could also define right multiplication. In fact, I challenge you viewers at home, looking at what we just did, what would you do if you wanted to define right multiplication rather than left multiplication? So now we're back at the inquiry phase. Okay, so if we developed all this technology for what we called left multiplication, what is the analog for right multiplication? And I'm going to leave that to you because I know that you're super what I would call curious and creative and intelligent, and I know you got a lot of great ideas. And I'm going to start leading you through the process of kind of tracking mathematical inquiry. All right, we're going to conclude this video, but before we do, I want to just kind of clean this up a little bit. Let me put some page numbers on my notes. So this was page 1. Then we had page 2. Then, of course, we introduced some terminology, what I would call nerdy notation on page 3. Then we extended that nerdy notation to kind of answer our first question on page 4. And finally, we have page 5. I should do a better job of tracking my pages as I work. And then the last thing I'm going to do is I'm just going to kind of track my own progress through this multiple representations. Here, I wanted to answer the question, what is multiplication? I'm going to ask myself, have I found multiple ways to answer that question? And I'm going to do this. I have described this in words. I used both what I would call intuitive and formal language. I've actually drawn some pictures to represent this. I have at least 2 questions, so I'm interested and intrigued by this. I'm allowing myself to be curious. And I've also actually started to represent these in symbols, meaning to say writing it on the page. And I can extend this. I would actually claim that I am ready to, what I would say, abstract away. So note, general, we can develop perhaps a general notation for multiplication using these examples. Okay, so when we say product is equal to a left factor times a right factor. So this is what we call product. So that's P. Here we're going to call the thing on the right, we'll call that the right factor. We'll call the thing on the left the left factor. And we'll call this the multiplication dot symbol. And we'll say that left multiplication takes R to start and hits on the left by L. All right, so I challenge you at home. If left multiplication takes R to start and hits on the left by L to produce P, what does the right multiplication do? How would I interpret this general idea using counting? Well, I would say left multiplication, I start with groups of, then I take L of such groups and I want to know how many total units. If I have L groups, each of which has R units, total number of units would be P, the product of that. Come up with your own ideas about right multiplication, and we're going to use this discussion in our kind of discovery process, exploration of what we call distributivity, which is kind of a prereq to some of the or foundations for some of the stuff that we do in algebra. All right, y'all, you're geniuses. The harder you work and the more ways you look at it, the bigger your math brain gets. Remember, math is all about making mistakes, correcting mistakes, asking questions, multiple representations. It's not about procedures. It's about curiosity and exploration. Great job, y'all. See you in the next video.